our work as follows today. Introduction first, as model, problem of our delay, our proposed method, and summary for the last. Various technologies have been studied and implemented for high-performance LCDs. Recently, ultra-light size and high resolution, such as ultra definition, has appeared in the market. Moreover, for high image quality, higher frame rate driving, over 120 Hz is also applied to these LCDs. However, there are some problems in the LCDs. Among them, I'd like to focus on two main issues. One is the short gate turn time, and the other is heavier electrical load of gate and data lines. As shown in this figure, the higher frame frequency and resolution become, the shorter gate turn time is. So, optimized driving scheme is necessary to these ultra-large size, high resolution, and high frame rate LCDs. Dual-bank driver scheme is widely used for ultra-large LCDs with high resolution. Even though the dual-bank driving is optimal one, we want to challenge the dual-bank scheme. And what is single-bank scheme? The single-bank scheme can reduce the cost for drivers and additional electronics for them. In addition, we can have more degrees of freedom in a design perspective. So single-bank driver scheme is more desirable than dual-bank in these aspects. From now, I'm going to propose a single-bank scheme that keeps image quality. Left one shows the SID model of metal line in our work, expressed as a distributed circuit with T models. At first, we investigate how many T models are needed to describe the metal load line precisely. Right one shows the signal in the RC line according to the number of RC T models. As shown in this figure, there is no difference in delayed signals if we use more than 6 T models. So we made the distributed circuit models of gate and data line using T models by considering aspect ratio of this plane 16:9. Therefore, gate line can be expressed with 16 T models like the first one, and data line can be described by 9 T models as second and third ones. As shown in this figure, 2 T models can be expressed like this one, the series combination of resistance. Finally, data line can be made with 17 registers, including 2 registers with half resistance and 16 capacitors. Data lines can be expressed like this, and if single-bank driver scheme is applied, power source is located only one side. Now at this slide, I'm going to explain the problem of RC delay. If we know the TV characteristic of LCD, we can extract the luminance of 16 times 9, that means 144 regions across the screen. And we can finally calculate the uniformity of LCD by using this equation. This figure shows the luminance map of LCD when dual-bank gate driver and dual-bank gate and data driver scheme are adopted. The LCD displays through a level 128 in this case. The maximum luminance was 99.8 candela per square meter, and uniformity was 95.8%. So there's no problem when dual gate and dual data driver scheme are adopted. However, it is quite another story when single-bank data driver scheme is adopted. In this case, due to the absence of data driver ICs at the bottom, and data signals are delayed severely by heavy RC load of data lines. In the left one, it can be seen that data signal at the bottom is distorted severely, like this. Finally, the pixels are charged by improper data voltages because of distorted data signals, as shown in the luminance map. Due to the heavy load lines, we can see that uniformity is decreased remarkably. So when single bank data driver scheme is adopted, screen uniformity becomes worse. Uniformity is decreased by as much as 27% from 95% to 68%. Therefore, it is necessary to alleviate this non-uniformity problem. Here is the concept of our proposed method. If we can make enough charging time for pizza, we apply, and compensate for IC delays of data and gate line. Single bank data driver scheme can be successful with no image degradation. To resolve the problem of insufficient pixel charging time, we apply the pre-charging method to SID. These are the gate signals when pre-charging method is applied. To make one line time longer, within the limitation of one frame time, a single line must share its charging time with the other lines. In our work, because alternate column driving scheme is applied, we use the gate line as pre-charging tool, this one, to make each pixel is pre-charged with its own color. And this figure shows the luminance map of SID when pre-charging method is applied with dual bank gate and single bank data driver scheme. SID displays grid level 128 as well in this case. Now you can see that the maximum luminance is increased by 116 candles per square meter. Comparing with conventional single bank data driver scheme because of increased charging time. However, as you can see, screen uniformity is even worse. The second one is line time optimization method to improve uniformity. This figure shows the simple diagram of line time optimization method. LTO, that means line time optimization method, is to modulate gate turn time depending on the position of LCD. At the region A, there is nearly no IC delay, so the turn time can be reduced in some degrees. At the region B, there is severe IC delay, so gate turn time should be longer for enough pixel charging. Like this manner, as much as gate turn time reduced at some lines, the turn time can be increased at the other lines. And this figure shows the luminance map of LCD when LTO is applied with dual bank gate and single bank data driver scheme. LCD displays grid level 128 as well in this case. Now you can see that uniformity is increased comparing with conventional single bank data driver scheme. But the uniformity of horizontal direction is still poor. Due to the heavy RC load, there is a severe deterioration of gate signal in the gate line. We thought that this gate signal caused poor horizontal uniformity. So to alleviate poor uniformity in the horizontal direction, we also apply horizontal line delay compensation LS. And this HLDC is proposed by Dean McCartney. The concept of HLDC is to control the rising edge of data signal according to the horizontal position of LCD. This figure shows the concept of HLDC. According to how much delay the gate signal is, the timing of horizon transition is shifted. This figure shows the luminance map of LCD when HLDC is applied with dual bank gate and single bank data driver scheme. SID displays for level 128 as well in schemes. Now you can see that uniformity in all direction is improved comparing with conventional single bank data driver scheme. Here's the comparison of proposed method with conventional dual bank and single bank data driver scheme. You can see the proposed method can increase the luminance as 105.2 candela per square meter and improve uniformity as 95.3% comparing with conventional single bank data driver scheme. Comparing the proposed one with conventional dual bank data driver scheme, it shows the difference between them, and if the luminance is higher than conventional dual bank scheme, dual bank case. Now, let me summarize my talk. We propose optimized driving scheme for high image quality, SID with single bank data driver scheme. To compensate for insufficient charging time, we used pre-charging method at first. Next, to compensate for other delay of data line, we used LTO so that vertical uniformity is improved. Finally, to compensate for other delay of data line, we use HLDC. In conclusion, we can make the screen of LCD totally uniform. We are confident that our proposed method can achieve high image quality of LCD. Thank you for your attention.
This paper is open for questions.
In this simulation, did you consider the effect of safety? I mean, you just calculate the voltage level at the cost point of data gate drive, or you included the variable resistance of TFTs and you calculate the voltage across the pixel train distance.
We don't need to consider it because we have no TFTs in this model, just registers and capacitors.
Okay, thank you.
Hi. I just wanted to thank you. I'm Dick McCarthy. Thank you for your comment and doing good work. Appreciate it.
I have a question. I wonder that the first gate pass, the positive pass duration, and the final gate pass duration. What's the difference?
I'm sorry.
The gate driver ultimately pass to drive I9. So the first pass duration and the last pass duration. How the positive pass time.
You're saying when you change the pulse duration, you're changing the forward edge or the trailing edge?
Not straight ahead to the device, but the pulse length.
Pulse,
Pulse.
pulse width.
Life.
I'm not sure any of this. We might want to. It's only a half an hour. We can do other interviews. Maybe easier. We can sketch it out. Sorry.
Can you go back one of the slides? I think it was 13.
13?
This one, 14.
This one.
Yes. So in your approach, if you look at the corner, right, on the upper left and upper right corner, there is significant non-uniformity in your part, the proposed single bank driving scheme. Yeah, right there, right?
Yeah.
That non-uniformity seems to be much greater than the rest of the pixels, right? So do you have any theory on why that is the case?
You mean why this one and this one is different?
No. I mean, why in your single bank writing scheme part, the upper left and upper right corners
Yeah.
have, no, the lower part. Is there a limit in your algorithm approach that cause the corners to run out of
I know
compensation?
This purpose one contains all of these three methods, and we just optimize the luminance by this method HLDC based on this line. So we can make the uniform luminance map, but in here, because of the pre-charging method, the luminance is to increase, I think. So it is more brighter than other side, other region. But you see this difference can, this is, you can think this, they are a big difference, but there's no difference in luminance. In fact, actually.
Okay, all right, we can talk. Thank you.
Thank you.
Okay, if there are no other questions, I think we can go on to the next paper. Thank you. That's all. Thank you, speaker.